Hello everyone, and welcome to another episode of BMED 202. In this episode, I will show you how to graphically solve for resultant forces and the equilibriant forces from these vectors that you are seeing here. Now, you can graphically solve for the resultant of any number of forces acting on a single body via calculations or via the graphical method. In the last video, I explained how to graphically solve for the resultant force of a number of forces acting on a body using the traditional means, meaning drawing with a T-square and compasses, etc. Not compasses, sorry, but you get what I mean. Now, I am going to use the graphical method just the same, but using AutoCAD. It's the same principle, it's just that you have to learn how to manipulate the AutoCAD software so that you are able to come up with the same result. AutoCAD should give you a more accurate results, or give you accurate results as opposed to the traditional means. So the principle is the same. So let's start with this first force, or the first scenario. Now, the first scenario that we will look at is a scenario that involves two forces acting on a body, and the body will be in this position. So where the vectors meet, that's the position of the body. Now, one force is acting in this direction, another force is acting in this direction. Now the difference or the angle between the forces in terms of the direction is 120 degrees. Now, whenever two forces are acting from a single point, we use what we call the parallelogram of forces diagram to solve for the resultant forces. Let me show you how you do that. Now, you take the two forces. Let me recreate this diagram so that you can know how AutoCAD is used to create the diagram. Now, from the central point, you just pick a point. We put the line in the direction of the force, and we type the distance. Now, remember from the previous video, we transfer the force in distance and we draw it to scale. So for example, if we're using a scale of 1 to 1 as it relates to force versus distance, you will have 66 newtons being represented by 66 millimeters. So that's the scale. 66 millimeters equals 66 newtons. Now you can use whatever scale you like. Now I've drawn this, and based on the arrow, I need to select a 30-degree angle, or angles in increments of 30 degrees, and position the vector accordingly. So the second arrow will go 60 degrees in that direction, which is 120 degrees from the opposite direction, and the second force is 37 newtons, which will be represented by 37 millimeters. Now, there are multiple ways that you can use to get the arrowhead. I am choosing the simplest means. It doesn't matter. All that matters is that the length of the line is corresponding with the length of the force, or the magnitude of the force rather. Now I have my arrow. So this is the force, and just to show you the angle, let me pull on a angular dimension, and I normally put these in different layers. Okay, so this is the recreation, and you should have already known from previous videos how to get the numbers or how to write the text beside the vector. Alright, we refer to these lines as vectors. This is a vector, this is a vector, two vectors interacting at this point. Okay, pulling away from this point. So the parallelogram of forces is such that you are going to use these two vectors or these two lines to create two other lines which will be parallel to these lines respectively, meaning this line will have another line over this side being parallel to it, same distance, same magnitude, same direction. Likewise this. So let me go ahead and copy this line from the base, and I'm going to place it at the end of this line. I'm going to do the same with this. Let me copy. If you realize you have created a parallelogram, right? And the next step, and please note the layers that I'm using, I have prepped or pre-prepped rather a line for my resultant force. So this is the point where the forces are acting from. I'm going to select the line command and connect it to the opposite point of the parallelogram. So this is the shorter diagonal. Please note the shorter diagonal. In some cases, it might be the larger diagonal. As long as you're moving from the same point that the first two forces are moving from. So once you connect or draw the diagonal is representing the resultant force, and the direction is such that it is acting from the same point. So this is the direction. So you would put an arrow So this is the resultant force. You have graphically solved for the resultant force using the parallelogram of forces method. And I'm going to change these lines to construction lines. So basically what this diagram is showing is that if you have a force acting in this direction at this magnitude on a body, and simultaneously another force is acting in this direction with this magnitude on the same body, the body will in turn now be forced to move in this direction. And the magnitude, the new magnitude that will result as a result of these magnitudes and directions combining will be, let me go for an angular dimension, because not the angular dimension rather, the aligned dimension is the type of dimension that can measure diagonal distances. If you use a linear dimension, you will only be able to measure vertical and horizontal distances. Now this resultant force, let me change the layer. The resultant force, and please note, my layer is called construction for construction lines. You can call this layer anything you want. It's just for variation. This new force will be acting at a magnitude of 57.29 or 57.3 newtons. So basically what is happening, if you have a body and these two forces are acting on the body simultaneously with the respective magnitudes and respective directions in relation to each other, rather than the body moving in this direction or this direction, it will now move in this direction with this force acting on it. So that's the first video. In this series, we'll look at the next video that will be illustrating how you use the triangle of forces method to find the equilibriant force that is required to put a body in equilibrium. So stick around for that video. Remember to like, subscribe, and share the knowledge. Have a good day.